and we'll be starting in about 30 seconds or so. Hello, everyone. Welcome to this Wind Power Engineering and Development webinar, Practical Tips for Maximizing the Financial Impact of Resource Measurements. I'm your host, Nick Sharpley, Associate Editor of Wind Power Engineering and Development magazine. Thank you for joining us. Just a brief agenda before we start. This webinar will be available at windpowerengineering.com. A link to it and the slides will be emailed to everyone, along with a 5-question follow-up survey. So please take a few minutes to complete that. And at the end of the presentation, we will have a question and answer session. Of course, not everyone that wanted to watch today's webinar could do so, but you can help them learn from it by tweeting key points and takeaways you think are important. In your tweets, be sure to include the hashtag WinWebinar. After the presentations, I'll read the questions that you and the audience have submitted. You can do this by typing them into the questions box in your GoToMeeting panel that should be on your right side of the screen. We'll try to answer as many as possible before the hour is up. Let me tell you a little bit about our speakers, then I'll turn the microphone over to them. As head of section for DNV KEMA's Wind Energy Analysis Group, Katie Briggs manages staff providing wind resource and energy assessment services to developers, utilities, investors, and government agencies. She is responsible for evaluating wind resource assessment methods, estimating wind project production and energy losses, and analyzing project uncertainties. She has a master's and bachelor's degree in physics. Robert Poore is Vice President of Business and Service Development for DNV KEMA Energy and Sustainability. His more than 30 years of experience in the wind industry includes domestic and international project feasibility analysis, resource assessment, and technical and economic due diligence. He has served as an independent engineer for numerous wind energy projects, working for both equity and debt investors. Mr. Poore's experience also includes wind energy, economics, and technology training, engineering design and test management, technology transfer, and organizational management. With that, let's start. Katie and Robert, the microphone is yours.
Thank you very much, Nick, and thank you all for attending our webinar. This is Robert Poore, and as many of you know, our firm has been working for many decades with developers, debt and equity investors, and others to assess wind project performance. For much of that time, we focused on trying to get the P50 energy estimate right, and doing that in particular through additional measurements, also understanding losses. Over time, we've learned that there's also real value in reducing uncertainty. Decreasing uncertainty increases project value, and it does that through allowing larger debt sizes on projects, also by making projects more attractive to equity. If you've got lower uncertainty in your project, equity should find that a more valuable proposition than a project that's highly uncertain. This webinar is going to focus on these points. I think Katie's put together a very interesting presentation and group of examples for you. But there are also strategic applications for the contents of the webinar. If you're bidding on a PPA, for example, if you can reduce the uncertainty in a project, you may be able to offer more competitive pricing and potentially have a better chance of winning a PPA. And I think we all know that finding PPAs and winning them is particularly challenging in our current environment. Also, if you're buying or selling projects, and there's a lot of that happening right now, you may be able to see opportunities to increase the value of the project that perhaps others don't see through additional measurements and reducing the uncertainty in the energy assessment. With the extension of the PTC that allows projects to get completed and term financed in 2014, it's provided a unique opportunity to make additional measurements and have time to actually have an impact on the uncertainty and on the value of projects. The extended measurement period is important because having extended measurements adds the most value to projects. With that, I'm going to turn it over to Katie to provide details and examples of how resource measurements enhance value. And I look forward to talking with many of you about how our resource measurement and energy analysis teams can help you maximize the value of projects you're examining. Thank you. Katie, it's all yours.
Thanks. So let's get started. Okay. Trying to click to the next slide. There we go. Here's the line. So we'll talk about measurements and how they increase value. The short answer to that question is they increase value by reducing uncertainty. And so we'll talk about how to do that, and we'll give some case studies, talk about the conclusions, and have a question and answer period. Going to the next slide. There you go. So how does measurement increase project value? It does so because when you add measurements, you reduce uncertainty, and when you reduce uncertainty, this improves project value. Specifically, if you're financing a project, uncertainty increases the debt size. So let's talk about how we define uncertainty. This plot on the right shows the probability of occurrence for different energy production values. And so the P50 is the median estimate for the energy production of a project, and the P99 is used as a metric for the uncertainty. The closer the P99 is to the P50, the less uncertain the energy estimate is. And this one-year P99 is used to size the debt on the project. Specifically, typically a debt service coverage ratio of 1 is required at the one-year P99 level. So what that means is if you produce the energy production at the one-year P99 level, the revenue that comes from that level is matched to the amount of debt to be paid for your debt payments for that, for a particular size. So when those two factors match, you have a debt service coverage ratio of 1. So if you can reduce your P99 and by additional measurements, that will increase the P99 to the next level. There we go, there's the slide. So by adding measurements, the P99 gets closer to P50, and it's usually a higher number. So with that revenue, you can pay more debt, and then that increases your overall debt size. Why is debt size important? Because it increases the value of the project, and how it does that is a couple of ways. But mainly if you borrow, when you have a larger debt size, you can borrow for less than the underlying return on the investment and still get a good amount of value out of the project. So in other words, there's less money coming out of your project to get in and get value out of this investment. So that's why a larger debt size is valuable. In some cases, you can also reduce the required rate of return of the investment by reducing uncertainty. What this means is that your project is more attractive to lenders or investors, and therefore it's more competitive in the market. Even if you're not financing the project or you're putting it on your balance sheet, reducing the uncertainty is still valuable. And what that is because projects are expected to meet their P50. So you want to have projects, you want to reduce the uncertainty so you're more likely to meet that P50. Nobody wants an underperforming project, and if you had an overperforming project, that's great, but if you financed, it probably means you left some money on the table. So these are the reasons why you would want to add additional measurements to reduce uncertainty and how it increases the project value. to get this all to work out, you're going to need to make sure your measurements are done right. And that often means measuring for at least a year with each additional measurement. So what I'm saying is time is of the essence. If you've got a project that you want to get constructed this year so that you can meet the PTC and then finance next year, you want to start your measurements now so they're ready and have a full year by the time you get the financing completed. So how do you go about this? The first step is to assess the uncertainties. And I'm trying to advance the slide. There it goes. By assessing the uncertainties, you'll want to look at the existing measurements that you have. And this plot shows the different categories of uncertainty you would have for an energy assessment for an example project. First, looking at the measurement accuracy, you'll ask a few questions. And these questions are, what is the sensor accuracy? What interference might I have from the tower effects or echoes from a SODAR, or is there any degradation? And that will help define what the uncertainty is in the measurement accuracy. You also look at what the validation methods was used. You'll want to check out the documentation if that was well done and if there was maintenance, and that will help you identify what the uncertainty is for that category. The next category is the vertical extrapolation. So this is the uncertainty associated with estimating the wind at the heights that you're extracting energy from. So you'll ask, what is the measurements at height that I have relative to the hub height? What's the uncertainty in that estimate and extrapolation? And then also, how well do I know the conditions across the rotor? Do I have measurements for that? The historical wind resource uncertainty is associated with estimating the long-term average wind speed. So you'll want to know and assess this through what measurement duration you have on site. You may be using correlation to a reference data to extend your wind period to represent a longer term average. And you'll want to make sure that that's a consistent reference site. Future variability is another uncertainty, and it just represents the variability in that we don't know what the wind will be next year. It could be a high or low wind year, so that adds some uncertainty and variability to the energy production estimate. And it's usually defined based on where the project is located. Certain regions tend to have a higher or lower annual variability. The next category is spatial variation. And so this is the uncertainty of estimating the wind flow across the project. It's dependent on the quantity of measurements. It's also dependent on how representative those measurements are of the project and the turbine locations. You'll consider the complexity of the terrain and the flow, and also the accuracy of your flow modeling to assess this uncertainty. Energy losses are another uncertainty. So you'll take a look at, of all the losses here, what is the uncertainty around on those factors. Once you've assessed the uncertainty, you'll want to look at what you can do to reduce it. So that's step 2. For measuring accuracy, things you can do to reduce that are to properly select the equipment for your site, use industry standard installation techniques, make sure you're taking good documentation and conducting data validation in a sound manner. You want to be monitoring, maintaining the equipment. So that's how you would address that issue. To reduce vertical extrapolation, you'll want to make sure that you're measuring higher and across the rotor. That's the best way to reduce that uncertainty. The uncertainty of estimating the long-term wind resource is based on measuring longer. That's how you would address that. It can also be helpful if you can overlap your measurements with other towers you have nearby. For example, if you have a few miles away a project that you're developing that has a 7-year tower, at your new development, you want to make sure if you can, overlap those measurements in time so they can be used to extend the period at each. With regard to future variability, you can't do anything about that. It's not within your control. The wind will change, and that's just a matter of fact. So you just identify it and move on. But you can address spatial variation, and you do that by measuring in more locations and measuring in representative locations. With regard to energy losses, that's a hard uncertainty to address in the pre-construction phase. What you can do is it helps if you can measure across the rotor. We're seeing that gives more information into what the wake losses will be at the site. So knowing those conditions helps. But otherwise, a lot of the energy losses, those uncertainties are mitigated contractually. So now you know what you can do to reduce uncertainty. How do you get to a good plan and an effective plan? Step 3 is to focus on reducing the largest uncertainties, because that's where you will get the most value out of this process. So on the left here is a pie chart that shows a breakdown of wind speed uncertainties for a particular project. In this case, there's a large spatial variation uncertainty. When you look at how that spatial variation uncertainty impacts the overall energy uncertainty, you'll get a pie chart that looks like this. And you can see the spatial variation uncertainty has grown its piece of the pie. And why is that? When you combine uncertainties on wind speed, you square them. And when you square big numbers, they get bigger. When you square small numbers, they get a little bit bigger, but not as big. So that's how these larger uncertainties end up having a disproportionately large impact on the overall energy uncertainty. So for this site, addressing the spatial variation, you'll get the most uncertainty reduction and then the most value out of it. So before getting into some of the case studies, let's dig a little bit deeper into the vertical extrapolation and spatial variation uncertainty, because these are the uncertainties that tend to be largest for projects, but also the ones you have the most control over and you can reduce by measurement. So vertical extrapolation, it's becoming a bigger issue. And this is mainly driven by the fact that the shear and veer across the rotor, we're getting a better look at what's really going on across the rotor through tall towers, SODARs, and LIDARs. And what we're seeing is that there are some pretty interesting shear profiles that are going to affect the production. And if you don't measure that, you won't know that really what the production is going to be like. So as we're seeing more tall hub heights and larger rotors, this effect is exacerbated a little bit. As illustrated in the figure on the right, the Met Tower, 60 meters in this case, only reaches a fraction of the rotor span of this 100-meter hub height tower. So you would probably estimate a shear profile that looks like this, but in actuality, it might look more like this. So it's in certain conditions, particularly stable conditions, we're seeing that the shear profile, what we would typically estimate, isn't what is actually going on. So you'll want to make sure you have measured that so you can account for it properly. Another important uncertainty is the spatial variation. It's one that tends to be large at some projects, and you can address it by adding more measurement locations. We estimate the flow across the site using modeling, but those models will need good inputs. So that's why you'll need to measure in multiple places. Modeling is good, but it can't do miracles. So that's why we really encourage measurements in order to get any reduction in that category. So let's take a look at some scenarios and case studies. We'll look at two. One is a Midwest site with a 100-meter hub height, and the other is a complex terrain site. We will look at assessing the uncertainties. That's step one of the existing campaign. What's the situation, and then start looking at what can we do about it. How can we assess the potential measurement scenarios, what uncertainty reduction will be achieved through those cases. We'll put that uncertainty reduction in a pro forma model and see how it changes the debt size and net present value. So let's get started. The Midwest example is a 60-turbine project. The layout is shown on the right. It's a 100-meter hub height. There are 3 60-meter towers on the project, shown here. And if you're developing this, you've decided that this is going to be the project you're going to fast track for to meet the PTC deadline this year, get construction going this year, and get financing going this year. So you're wondering, how can I get the most value out of this project? What can I do? You've already got a 5-year period of data on site, so that's good. And your first step will be to look at the overall uncertainties for this project. So here's the breakdown of uncertainties for this project. You would like to address the largest uncertainty because that's where you get the most value. But unfortunately, it's the future variability uncertainty. You can't do anything about that. So you're going to look elsewhere. The historical resource uncertainty is the next largest, but you've decided we're going to, you're going to get this in the ground or start it this year to get the PTC. So you can't do much about that other than wait. And then the vertical extrapolation uncertainty is pretty high here. So let's address that. And how can you do that? Let's look at some measurement scenarios. You can do nothing, just continue measuring with your existing campaign, which would be the base case scenario that we'll compare against. Or you can install a 100-meter hub height tower at this location. You might be planning to do this already because you're going to conduct a power performance test, and so you're going to need that hub height tower anyway. Or you may want that tower to be the SCADA tower for operations. Another scenario, you could look at renting a SODAR for a year and putting it here. It could also turn into something that you use for the operations phase. Or there's a third option is maybe you just want a shorter rental and see what that looks like if you just rent the SODAR for 6 months. So those are the scenarios. Let's look at the results. And what is shown on this plot is the incremental cost that you spent for the measurements, including the equipment and the analysis and monitoring, and then the incremental value, or the change in net present value compared to the base case, and that's in the red bar. So what you can see here is you spent a few $1,000 and you got about a little less than $1 or $2 million back in change in net present value, depending on the scenario you chose. You can see the shorter term 6-month measurement had less than half the value, but it's also lower in cost. The Met Tower and the SODA had very similar change in value and a little bit different cost. You can see this presented in the next table. The top 2 rows are the values you saw for the chart before. The third row is the P99 P50 ratio, and you can see it didn't change much for the different scenarios, but little changes had quite a big impact on the debt size. So here's the change in debt size in the last row relative to the base case. And I will get to the assumptions and the costs that we use in these scenarios at the end, but wanted to kind of show you where we're going with this. So that's the Midwest example. Here's the complex terrain example. You have a project that looks like this, and there are 3 Met towers, 60 turbines, hub height of 80, They're all 60-meter towers so far. And you have a 2-year period at each of the towers, and you've been able to use a reference data set to extend that. You might look at this case and say, wow, they really haven't characterized what's going on at the site, and you're exactly right. You might think, oh, well, this isn't a common case. In reality, we have seen projects that have inadequate measurements going to financing. And they're leaving a lot of, they're not getting all the value out of it that they could. So while this may look like an odd example, it's not that uncommon, unfortunately. You also get into this kind of situation where you have a few Met towers that don't fully represent the project when you have, your layout changes due to environmental restrictions in one area where you plan on developing or landowner restrictions. So your measurements should often move along with your layout as it changes. But how would we deal with this project? How would we get more value out of it? We first start by assessing the uncertainties. In this case, the spatial variation is the largest uncertainty, so you're going to try to address that. And we'll go through the measurement scenarios that you would do to address that. In this case, we're looking at installing 1 additional measurement or 2, or you're going to install 3, or you're going to install 4 measurements. These measurements could be towers, SODARs, LIDARs, depending on what you've got going at your site, the conditions, you might pick one over the other. In this scenario, I'll go through the Met Tower case. If you just added 1 to 4 60-meter Met towers, how does that change your project value? And here are the results. So as you add a tower, the incremental value, the change in net present value, is between about 3 and 8 million relative to the base case of not adding any measurements. And the costs, are a fraction of that. So there's really a payback. It's really hard to put down cost and measurements up front, particularly if you're not sure the project's going to go through. But in a lot of these cases, when you're getting close to building a project, you're confident, it's going to go through, putting that cost into measurement, while it is at risk, it's not that much of a risk. So especially as you're getting close to finishing a project is when you want to start thinking about, okay, what measurements can I throw at it to eke out that last bit of value? This next table shows these values for the plot. Here you can see the P90, P50 ratio changed a little bit more in each case because we started with a pretty uncertain project and was able to continue to reduce that uncertainty. And we're also showing the change in debt size relative to the base case. So you can look at these if you'd like. There are diminishing returns to this. You could measure at every turbine location, and that would be great, but expensive, and you won't get, at some point you start losing the value. So this plot shows that with each additional measurement, your uncertainty is reducing to a point. At about 4 or 5 additional towers, in this case, or SODARs or LIDARs, you wouldn't be reducing the uncertainty that much more with each additional measurement. And why that is you're probably running into, you reduce the spatial variation uncertainty, but you're running into some other uncertainty that you're not addressing. So you've gone from the spatial variation uncertainty, running and driving the uncertainty analysis to some other factor. So you might start looking at that. But there are other reasons why you would have potentially diminishing returns. And this plot shows the change in your P99, P50 ratio on the x-axis. So this is your uncertainty on the x-axis against, on the y-axis, the project 20-year net present value. And as you increase with each additional measurement, you can see the net present value going up until you get to the fourth and fifth additional measurement, it starts to flatline. And what's happening here is that you've reached a different debt sizing limit. Your debt size is no longer driven by the uncertainties, but it becomes driven by the P50 value. And there's often a 1.45 debt service coverage ratio limit on the P50. So that's something to look at. Where are you for your project? Are uncertainties driving the debt size, or is it something else? So here are the assumptions I promised you on our cost-benefit analysis. It's a 20-year project life, leveraged IRR of 14%, a discount rate of 12% for the values we showed you here. But we looked at a broad range of discount rates, and in those cases, the value of the measurements was positive over those range and discount rates. But it's something you want to look at in a case-by-case basis. We talked about the debt service coverage ratio limits. We used a 5.5% interest rate and a debt term of 17 years. The cost assumptions are shown here, and then we provide a kind of a typical industry range. Of course, these costs will really vary based on the location, what you're buying, all sorts of things, but we wanted to give you some information you could reference if you wanted to get a sense for variation in costs. And now the key takeaways, things I want you to come away with. The step to how you improve your project value is you first start by assessing the uncertainty. You'll then want to focus on reducing the largest uncertainty. That's the most effective approach. And how you do that is you measure longer, you measure higher, and you measure in more locations. And you'll want to look at this and conduct a project-specific analysis. This is something we can help you with. If you want help understanding what the uncertainties are, how they would change with additional measurements, we can help you with that. We also can provide measurement guidance, procurement, and installation of measurements if that's of interest. And we can do this cost-benefit analysis to really see what project value you can reach and how to get that. So the takeaways and conclusions: increasing measurements reduces uncertainty. Reducing uncertainty improves project economics. We've looked at a lot of cases. We've just shown a few here, but the economics are pretty compelling in a lot of cases. And the time to do it is now, particularly for those PTC projects, is you'll need a year measurement to really get that value out of the project if you're going to finance it next year. So let's get this going and let us know if you can help. I want to thank you, and we'll take some questions. And thanks to Robert and Kim for the help on this as well. Nick, back to you.
Hey, thank you, Katie. I'm sure the audience found this as useful as I did. So we're just going to wrap up with a few questions. The first question is, how much does the measurement accuracy typically impact the overall uncertainty? For example, does it pay off to use more expensive but more accurate anometers? Excuse me, sorry.
Yeah, to answer that question, having a good, maybe spending additional money on first-class anemometers is good, but often that may not be what's driving your uncertainty. If you have a project that has 60-meter towers and 100-meter hub height, for example, you'll really want to address getting taller measurements, because that's probably what's going to be driving the overall uncertainty. But you still want to make sure that all your other, all your other equipment and your measurement accuracy is good. But often it's really a kind of a case-by-case basis that you want to focus on getting getting the most reduction by the proper measurement method. And in some cases, that's anemometer accuracy and addressing that. In other cases, it's more towers. For the Midwest example we showed here, we looked at how the measurement uncertainty, if you reduce that, what the overall change would be. And because there was fairly low uncertainties under the other categories, if you did have a good quality measurement system and good maintenance and good data, that would really drive the uncertainties. So in short, yes, it's good to make sure you're using good quality data, and a lot of times it's just make sure whatever you're using, you're monitoring it and you're maintaining it. But also don't forget there's other uncertainties to focus on.
Okay. Okay, the next question is, do SODAR and LIDAR have the same impact on the uncertainties, especially in an NPV aspect?
That's a very project-specific question. In some cases, a LIDAR would give you more uncertainty reduction and therefore more NPV. In other cases, the SODAR would do a better job. It really depends on, for each particular site, which which device will give you better data recovery. Each device has its own data recovery issues. For instance, SODAR you won't measure in the rain. So a rainy site you might have lower recovery there. For a LIDAR, if you have a problem keeping a remote power system going, then you might have lower recovery. So it really depends on what the specifics of the site are and what the data is. And so what is the recovery that you're getting at hub height and across the rotor?
Okay, thank you. The next question is, can DMV KEMA comment on situations where additional measurements end up reducing the P50 value?
Yeah. In our scenarios here, we kept the P50 the same regardless of what measurement scenario you were looking at. In reality, the P50 will change a little bit. The more you know and from data and that when you rerun the analysis, the P50 will change a little bit. It may be higher, it may be lower. By adding additional measurements, what you are guaranteeing is that you can increase or decrease the spread between the P50 and the P99, and that will typically bring up the P99 level, and you get additional debt size. If your project is, if the debt size is really driven by the uncertainties, change in the P50 is not going to drive the debt size. It's going to be the P99 and how it moves that will drive the debt size. But that is a very good point. The P50 can change.
And this is Robert. I would add that the potential for the P50 to go either up or down exists. We've seen both circumstances. If the P50 goes up with additional measurements, if you don't make those measurements, you're leaving that potential on the table in your discussions with whoever you're talking to about the project. And if it ends up going down, the uncertainty will also go down. And in our experience, generally, if it's a leveraged project, then the project value either goes up or stays roughly the same depending on the circumstances of the project. And if it's not a leveraged project, then if you have a more accurate P50, your long-term relationships with your investors are improved as the project meets those expectations better.
Okay, thank you. Next question is, how do you quantify a change in future wind variability when given just on-site data or a longer-term reference station?
Yeah, to really accurately quantify the future variability uncertainty or the interannual variability, ideally you would have hub height measurements, wind speed measurements for 15 plus years at your site. I have not seen that yet. So what we do to estimate that uncertainty, or if it were to change, it's just it's a given. The wind is what it is, so we can't really change it, but we can do our best to assess it. And how we do that is we'll look at long-term data sets and see how the wind speed is changing from year to year. And in some cases, we don't have the best data to do that, or we don't have the data on site to really estimate that. So in short, that uncertainty doesn't really change. You can't change it. It's just a matter of can you assess it in the best way. And the data to do that is not typicically available.
Okay, thank you. The next question is, you seem to indicate SODAR is as bankable as Met towers. Is that exactly the case?
When we get SODAR data, we use it. We will consider the uncertainties associated with it, and we do recommend that you place the SODAR next to a tower to confirm the accuracy and understand its relationship to a Met tower. But it can be valuable, and we use it when we get it. It's always better than not having that information. It's particularly valuable when you're looking at, you have a high vertical extrapolation uncertainty, shear uncertainty, and you need measurements higher than, say, a 60-meter tower. So it's really useful in that aspect, and LiDAR in a similar way.
Okay, thank you. The next question is, what is the suggested distance between Met towers?
It's not just distance that plays a factor in how to site your Met towers, but that is one consideration. I generally think of it more in terms of I want to make sure I represent the conditions at my turbine location. So I will be looking at placing measurements in the high elevations, the low elevations, in between. If I've got, a lot of turbines in the north part of the project, I want to make sure I've got measurements there in the south part of the project. So that results in different distances, between Met towers. So it's hard to say a particular distance. It will really depend on, how spread out is your project to start with, and what kind of characteristics and changes are you trying to capture.
Okay.
The other element, in addition to terrain, this is Robert, in addition to terrain, the other element that figures in there is vegetation cover and ground cover in general and overall exposure. Go ahead, Nick.
Okay, thank you. The next question is, how is the SODAR measurements incorporated into the resource assessment? Is it used as an input in the wind flow modeling?
Yes. When we see a full year of data, or at least 6 months, or we can extend the period. We often see SODAR data come in for analysis and an energy assessment, and it has 3 months of data at a particular location. It's difficult to turn that 3 months of data into an annual average without having fairly high uncertainties. So if we, particularly when we see longer periods of SODAR data in one location, yes, it'll be used in the wind flow model because that gives us some information about that location that we wouldn't otherwise have. But when you do see a short period of SODAR data, we'll use it to the extent we can to get a sense for, okay, for those 3 months, that location was, let's say, 5% higher than my other location. So we'll use that information, but there's some uncertainty, does that 5% relationship maintain, stay the same throughout the rest of the year, or does it change? So we'd like to see SODAR data and LiDAR data that have full years of data. That's when you really start to see it have the impact, and we'll use it directly in flow modeling. As with anything else, though, we consider the uncertainties of that measurement, like we do with Met towers.
Okay, the next question is, how much remote sensing data do we need to impact uncertainties?
Yeah, so I think the best is at least a year in a single location. After that, you may want to consider moving it to another location if you've got a fairly varied terrain site, or you don't have enough measurement coverage across the site. But really, to get the value, it's nice to keep it in one spot so you can see the shear changes throughout the year.
Okay, and this is a fairly long question, so I can repeat it if you need, but in your complex terrain case, you showed adding additional measurement sites, whether it be mass, SODAR, or LIDARs, to decrease the measurement uncertainty. Do you recommend co-locating the remote sensing devices within an existing met mass first? If so, how long?
Yes, we typically recommend you put the SODAR LiDAR next to the tower that you have on site before you move it to a new location. And how long you want to do that will depend on how long it takes to get a good correlation and understanding of the relationship between the tower data and the SODAR or LiDAR data. And that is typically 1 to 2 months. And we have a process that gets fairly detailed into the math of how to establish, when you've kind of hit that time period where you have enough understanding of the relationship and you can now move it to the next location. But I won't get into that math.
Okay. The next question is, how long would you need to measure across the rotor to make an impact, good or bad, on uncertainty and wakes at any one Met tower? What if you don't have 1 year worth of time?
Yeah, if you don't have 1 year worth of time, it's still worthwhile. You just won't see as much change in your overall uncertainty. Even just a few months tells us whether, let's say, the shear at a 60-meter tower extends up to 80 meters or 100 meters or across the rotor. So just within 3 months, we can see, at least in that time period, whether the shear conditions are increasing with height, or the alpha shear is decreasing with height, or it's doing something strange, or even what the wind veer is. And we can use those shear values across the rotor to better estimate what the production of the turbine would be, and also if there's, if the wakes are likely to travel further because there's less wind above the rotor to come in and replenish the wakes. So it does help. It's just when you get a full year, you get to understand if there's any changes throughout the different seasons, or if what you measured in those 3 months is representative.
Another factor there is the quality of the data collection and the robustness of the data sets. If you're looking at a short-term process, then data quality becomes even more important than for a longer-term measurement campaign.
Okay. The next question is, if you had the choice, would you rather go ahead with an additional 100-meter tower or a SODAR? Which one would turn out more interesting at the end?
Both would be quite interesting, I think. It will really depend. If I know I'm going to use that 100-meter tower for power performance testing, or I know I'm going to put that in for the operations phase of the project, so I can monitor the operations. That would be a good reason to do the tower. You could also use a SODAR or LiDAR to help in the operations phase. We recommend at least one permanent Met tower in the operations phase, but additional measurements from other devices are also helpful. So it would kind of really depend on what other uses you might have for the tower or the SODAR that you're installing. You also want to consider the cost. The 100-meter freestanding tower is quite expensive, but it's built to last. So you will, if you're ready to make that investment, that's a good way to go. If you're looking for, a shorter-term measurement, or you want to use, additional SODAR or LiDAR in the operations phase, you might move towards that approach.
Or you may have the SODAR or LiDAR in stock, so to speak, in your warehouse, and you want to put it to use.
Yeah, if you've got some equipment sitting around, you might as well use it. It's just a little bit of cost, and you get that value.
Okay, the next question. What is the shortest data period from either a tower or remote sensing unit that you would consider in a site analysis?
I would look at just about anything. A week is really pushing it, but you're really not going to get much value out of it. If there are 5 measurements across the site and there is a month from a 6th measurement at another part of the project, I would look at that and just see, relative for that month, relative to the other locations, was that higher location or lower wind location? And I would maybe use that qualitatively to check the wind flow modeling and see what it estimated for that location. But using it quantitatively, when you start to get into 3 and 6 months, then it starts to be used more, more quantitatively.
Okay. And when does it typically make sense to install towers versus SODARs versus LiDARs?
Again, that's a site-specific, question. Towers, the value in towers is they're relatively inexpensive. You can deploy them, and you kind of put them in one place, and you don't need to worry about it. We know what the typical uncertainty. We have a pretty good guess on what the recovery is going to be. It's a fairly common measurement and well understood measurement. With SODAR and LiDAR, you might want to use those when you have permitting problems for a tower. You can get a SODAR or LiDAR in much quicker. You can also get high measurements across the rotor, so you get higher heights than you would for, say, a 60-meter tower. There are a few more question marks on what the data quality will be because they're more affected by the atmospheric conditions. However, you don't typically need to worry as much about icing. Cup anemometers will typically freeze up, and so you'll lose some data in the winter. You might have some issues with weather for the remote sensing devices, but you won't have it ice up like a cup does. So it's good to have kind of a combination of these measures, these measurement types. And between a SODAR and LiDAR, it really depends on what you're going for. In some cases, one might be more accurate than the other, given the site conditions. So that's something to consider up front. And there are cost differences for all of these.
Okay, thank you. Okay, folks, we are running out of time. Once again, this webcast will be available for reviewing at windpowerengineering.com. You can follow Wind Power Engineering on Facebook, Twitter, and LinkedIn. This concludes our presentation. I'd like to thank everyone for their attention. Again, there will be a 5-question follow-up survey in the recap email, and enjoy the rest of your day.